We have no one on the other side. Curtis is usually there. Hello, Curtis.
Hello.
Okay, so we have homework due today. The new homework I haven't posted yet, but probably within a few hours. That's it. Homework 10. How was homework time, by the way? Pretty done smooth.
I think most of the one was number 7, the last one, but we've done it exactly in class, so I forget to
Okay. Okay. Remind me, what was it about?
find the electric field inside. You gave the polarization, so we had to calculate the
Got it.
potential first, and
Yes, this is pretty much
it was
the
very
same.
fluid.
Yeah. Okay. So we're going to change topics a little bit. Like we talked about polarization a little bit. Now we'll talk about conductors, perfect conductors. So this is next week, Monday. So we want to talk about conductors. I think it's good to talk about what I mean by conductors. Remember that we said polarization, very simplistic thought. So polarization is, how did we define this? Let's say, how did I define my polarization? Was dipole moment density, correct? So this was number density times the dipole moment per at point R, and this is dipole moment density. Right, and this was mostly permanent polarization. Right. And we also said something about induced polarization, and that's what we want to investigate. That induced polar, so this is permanent. And if it is induced, what we mean by that is that the material itself doesn't have any dipole moment, but if you apply an electric field, you can induce something, and that we will say is R. Usually it is frequency dependent, but we want to emphasize on that. So this is chi times the electric field at point R. And this is again at point R. As also for dimensionality reasons, we put an epsilon naught. It is good to think that in more general terms, this is equal to epsilon naught I as a tensor dotted with electric field, which is a vector. That means to say that here what we are saying is that if I apply an electric field, the material gets polarized in the direction of the electric field. But here what we are saying is that it doesn't have to be in the direction of the electric field. It could be along some other direction. And in general, the x component of electric field could give you y component of polarization. And that tensor is what this is. Again, we will try to keep it isotropic most of the time. So we don't have to worry about that right away over here. We also said if chi is introduced, or chi can be redefined, maybe that's the way to say it. So chi can be redefined in terms of a dielectric function, which is epsilon over epsilon naught minus 1. Again, if this was a tensor, this becomes a tensor. That's a unit dielectric. So how much you polarize the material is decided by the electric field and the property of the material itself. And then we ask what is the difference between an insulator and a conductor. Conductor has more free charges. There are more mobile charges available. And in the very extreme limit, if you say chi is infinite, that's what a perfect conductor is. So a perfect conductor would be, for our purposes, so a perfect conductor would be chi tends to infinity, which is often also said as epsilon tends to infinity. And what are examples of a very highly conducting material? Copper, copper, gold, silver, and all that. And what about a mirror? Right?
Yeah,
Is it a good conductor?
probably not.
Probably not, right? But notice, so but when I'm saying mirror, the immediate thing that comes to your mind is the glass that's there, right? But what causes the reflection? Is it the glass?
No.
So what is it that causes the reflection?
Something behind the glass.
Something, yeah? Like in the olden days, they didn't use glass, right? They used metal. I used to remember, like they polished the metal very. So if you polish the metal very well, it behaves like a mirror. Right? So, but then the polishing is a very hard job, a very expensive job. But then they realized that glass had this feature that it was very planar. It was very flat already. And then they realized that you just have to paint a very thin layer of metal on the glass, like usually the silver. So if you look at the back side of the mirror, there's a thin coating of metal. The light goes and basically it's the mirror, the metal that is doing the job of the reflection of the field, because glass, electric field, light penetrates through it. But at the end, or usually at the end, there is this metal that does the job of reflection. It is a metal that does the job of a mirror. So whenever you look at a mirror, think of it as a perfect metal. And that's what we want to think in that terms. As of now, we are just going to talk about charges, but soon, probably by next semester or so, we'll talk about actual light going and reflecting. But as of now, it is just a charge, and still we will see reflection properties there. Like usually an image, right? So whatever we're going to talk about today is going to be about image charges and how an image is formed inside a conductor. So that's the idea. But yeah, mirror is pretty much a metal form in this context, if you want. What's a perfect insulator? Say that again?
Rubber.
Rubber, yeah, it's a good insulator. What about a perfect insulator? Like chi has to go to 0, right? Epsilon going to epsilon naught. Right. For what material does epsilon is very close to epsilon naught? Huh?
I mean, a vacuum.
Vacuum, yeah, or air, pretty much. Like, what's the refractive index of air? Yeah, 4 zeros actually. So it's pretty much 1 and it is epsilon. So for our purposes, if you're working in 3 sig digits, it's pretty much vacuum for all or our purposes, if you want. And I said refractive index. Again, since we are going to talk about images and all, it might be of interest to see is why are we talking about images when there is no optics going on. It is good to realize that n is related. So the refractive index, it's not at all obvious as at this point why refractive index should be connected with epsilon. It is equal to square root of epsilon. And another thing I should say is that chi is so refractive index or I should also say what is epsilon. So what is chi called, by the way? Yeah, chi is electric susceptibility. And epsilon is electric permittivity. They're related to each other. And yeah, so chi is typically position dependent. That's not surprising, but always it is frequency. It is in the Fourier space. You would expect that here electric field is time dependent, correct? So you would say that the polarization should also be time dependent. That's correct. But then that relation is an integral because anything, an electric field from the past can also affect your polarization as of now. And that integral is converted into frequency because that's what we measure. We always measure the frequency part of this susceptibility, which is a Fourier transform of the actual susceptibility. So this is frequency dependent. And what that means is it can be complex. The moment you go to Fourier transform, remember your Fourier transform, so f of t is equal to d omega over 2 pi e raised to minus I omega t f tilde of omega and f tilde of omega is equal to minus infinity to plus infinity dt e raised to I omega t of f of t. The time dependent quantity, which is what happens in the lab, this is real. This is real, but the exponential in here is complex, which means to say that the frequency components of whatever we are measuring can be complex, right? So susceptibility of the electric permittivity can be complex. So this can be complex. It can be complex. It's not just can be complex. In general, most of the times they are complex. So that's one. And if it is complex, then we should realize what is this refractive index. It's usually dependent on the real part. It's the real part that decides. And the imaginary part is related to dissipation or absorption. The imaginary part of, so maybe I should write that here. the real part of chi is related to refractive index, which decides how much it will transmit, and imaginary part of chi decides absorption. And there are very intricate properties related to that. We won't do that in here. Yeah, a good point here is, I can give you an extra credit here. Extra credit. Read and read a little about Kramer's chronic relation. It involves the idea of analytic function in complex variables, and we will try. Let's not go in there. I'll just say that the real part and the imaginary part, or the refractive index of a material and the absorption of a material, remarkably, are the same in the sense one decides the other. If you know the absorption of a material, you can actually decipher everything about the frequency. In fact, experimentally, what you do is you measure one and you computationally evaluate the other, because that's much more reliable than actually measuring the other quantity again. So that's, so again, the simple idea is, what we want to take home is that the perfect conductor is chi tends to infinity or epsilon tends to infinity. But in that extreme limit, we lose a lot of properties, but the basic idea will still remain. Any questions at this stage? Any just general points? Okay, so let me specifically state what we want to do. So we want to have a perfect conductor. So this will be called method of images. In general, these are called. It's a whole topic. You can do this for various geometries, but we will do this for a simple metallic surface. So this is metal on the left hand side. That means to say that epsilon here is infinite. Think of this as a mirror. Everywhere on this side, it's a mirror or a perfect conductor. So this is a perfect conductor. And on the right side, so let's say this is z equal, and this goes all the way of that, right? So this is z equal to 0. So z direction is horizontal, and here this is vacuum. So that means air for our purpose. So this is vacuum or air for our purposes. That's pretty much. So perfect insulator, perfect conductor. Another property of perfect conductor is that since it can polarize things very well, electric field is 0. Correct? You might have used that property before. Also, electric field everywhere inside the conductor is equal to 0. That can be, why should it be 0? Because if it was not 0, and if there was a stray charge somewhere around, then the electric field will actually act on the charge and it will try to make it move. So whatever the charge is, because it is free to move, they will move around in such a way that the electric field actually comes out to be 0. In fact, it's not the electric field that tries to be Zero, it is the electric potential that tries to be uniform. Electric potential tries to be constant, but they're related, right? Electric field is equal to negative gradient of potential. So potential has to be a constant. This is the voltage we say, right? So this is a constant. So when we say in a lab, when you're doing, you sometimes connect some voltage to the conductor. So you're providing this phi. Phi can be constant. It could be 3 volt, 4 volt, and so on. But let's choose this to be 0. So that means to say we ground. Choose phi to be 0. Doesn't have to be. So let's choose that to be equal to 0. That way it seems like the geometry is not straight, right? So phi is equal to 0, basically it's ground. That means it's ground. So again, very simple scenario. We have a conductor, which means to say this is a mirror, right? In real life, how can you do this? Just keep a mirror there. And we set electric. We know that electric field is 0 inside the conductor, and further we set the voltage of that to be 0 by grounding that. And now what we want to do is a simple, very simple thing that we put a positive charge. Just a positive charge Q here. We place a positive charge Q at a certain distance A from the certain distance A. And what do you expect will happen? Nothing at all. Again, remember grounded, right? So ground is another way of looking at it, is that conductor is a huge reservoir of charges. And if it is connected to the ground, that means it has free access to that. If you bring in a positive charge, it will pull all the negative charges towards it, right?
Oh, okay. I thought you meant what would happen to this.
Oh, what will happen to this charge? Yeah, nothing. Or it will exert attractive force. Right? If there are negative charges here, it will feel an attraction. And so again, so if you put a positive charge, it's not very surprising that, okay, so this will get polarized in principle, or it will pull a lot of charges. And notice there will be less charges here, so there might be, one can expect that there will be more charges here because it is right in front of it. Right? And then there might be less dense as you go there. So, it's not positive charge, right? Sorry, negative charge. Negative charge. It's something like that. And we would like to investigate how much charges is that. I mean, how much charge will it pull on that? What really happens, and actually how much force is exerted on that. If there are negative charges on this will start attracting to this. And we would like to investigate that. And it turns out that there is a very simple mechanism to achieve this. Again, this uses the idea of optics. Now that we know electricity and magnetism is very closely related to optics, it may not be surprising, but earlier it was surprising that this should be an image. And now the idea is that, okay, instead of doing this problem, right, the properties of the conductor are not easy. So instead of doing this problem, what you do is change your problem altogether. So you have the same positive charge. That's your reference line now, not a conductor. You remove the conductor altogether. Instead, you keep that reference line there. So that's your A. And instead, you keep another charge, Qm, which we will call, so this is Q, and this will be Q image. The image charge, and we don't know how much should the image charge be. It will turn out that it is exactly negative in this case, but you could ask a more a bigger question, that what if this was curved, right? Then what is the image? Then it is no more exactly the same, like exactly like we do the lens and so on, and that can be easily done. In fact, the easiest is to keep a sphere here, and what is the image of that? But we won't go there. Let's just simply ask, what should the Q image be so the question is, what should this image charge be so that everywhere on Z greater than 0, the field is exactly that of a conductor. So the question is, so what should the image charge be so that electric potential phi and the electric field phi, once phi is defined, electric field is automatically defined, so we don't have to specify that. So that phi, and here for Z greater than 0, right? So this is Z, direction of Z is in this direction. For Z greater than 0 is exactly the same as that of a conductor at Z equal to 0. So this whole problem we want to simulate only on for Z greater than 0. Of course, Z less than 0 we won't be able to reproduce because we have put a charge. Furthermore, once you're inside a conductor, there is no electricity in there. There's no charges can stay inside there, so no electric field can stay there inside the conductor. So conductor is pretty barren, so nothing happens in there. And again, we will, like at this point, we are not going to prove this, but we will see that it is exactly the same distance that, actually, let's keep this A prime. So we can keep this also. Let's see, yeah, we can do it. So we want to keep an image. How far you want to keep an image? That's the point. To begin with, it is not obvious at all as to why should that work. But one hint is that electric potential has to be 0 on the conductor. So like if you have a positive and negative charge, it can balance out. So that's small motivation, but it's not very obvious why should that happen. So let's see at an arbitrary point first. So presuming that this is possible, so let's say this is the position R. So this is R, which is X, Y, and Z. Let's say the position here, this is 0, 0, 0. That's your origin. And this point here, let's say this is your Z-axis, remember? So X, you're on the X, on the Z-axis, so X and Y is 0. And this is plus A. And the position for the image, we are saying is 0, 0, minus A image. So we have two parameters we are saying. How big is the charge? We have an option. And where exactly we want to keep it, that's also an option. And what is going to be the guiding factor? We would like to have the phi equal to 0 everywhere on the boundary. So the question is, we require, so requirement, right? So require that phi everywhere on the, so what is this? So this is the XY plane. Right? So this is phi everywhere on XY. Whatever be your XY, but at Z equal to 0 should be, this is exactly equal to 0. to Z. When Z is set to 0, that means you're right on this plane. You want the electric potential, so the voltage when you measure, that has to be equal to 0. But everywhere else, it has to be identical to that of a conductor. But once this is 0, that is all we want to set. What is the general electric field due to this? Phi x, y, z. General. Or there are two charges, so it is plus q. And that is 4 pi epsilon naught divided by q over r, right? But r is, when it is at the origin, it is not at the origin. So you have x minus 0 squared plus y minus 0 squared plus z minus a squared. That's your distance from the observation point to the source point. So that's this distance. This distance is this point. That distance. But there is another charge. So the image, and this is plus 1 over 4 pi epsilon. We are assuming that it is a positive charge, but it will turn out that it will be a negative charge here. As of now, we don't know what it is. That's the equations decide that. So it's q image divided by x minus 0 square again, plus y minus 0 square, plus z minus a image. And again, our requirement is that this has to be equal to 0. Correct? So we just have to set this equal to 0 and solve for, hopefully, solve for q image and a image. Right? Seems like there is only one equation, but it's not just one equation because it's everywhere on the surface. Right? So there are many equations there. So let's see what other constraints we can build. So the condition is that when you set x equal to what did it say? Yeah, z equal to 0. So yeah, whenever I set z equal to 0, I have to add 0. So I have to set z equal to 0. So this is equal to 0. Whenever I set z equal to 0. So q over square plus y square plus z set to 0 sets a square. And similarly, set z equal to 0, which is the observation point on the second term also. That's x squared plus y squared plus a image squared. If this is equal to 0, I can put this on the other side. I can cancel out the 4 pi epsilon naught. So I write this as q over square plus y square plus a square is equal to minus q image over x square. This is true for any x and y. So to learn more about this, what we are going to do is this is going to come at a little sacrifice because I lose some information when I square it. So, right? Let me square this. So this is q squared over x squared plus y squared plus a squared. And notice this negative sign goes away when I square that. So we have to remember this, that we have squared. We will see some solutions coming which are not completely appropriate for what we are doing, that's because when we square it, we lose some information. Rewrite this as q square times, let me do this in 2 steps. So this is x square plus y square plus q square a image square, that's equal to q image square x square plus y square plus q image square times a square. Put all of this on the left hand side. I can write this as q square minus q image square times x square plus y square, or you can say x squared. Expand this out also, it's perfectly fine. And plus minus if you think of this as a function of x and y, which is what it is on the plane, right? X and y is this plane of the conductor. At every point, this has to go to 0. If that is true, that means there are infinite equations here. And which means to say that the coefficient of this has to be 0, coefficient of that has to be 0. Right? If a function is 0 everywhere, then the coefficient of x and y should be 0 independently. That means to say that this should be 0. So let me write that here. So q square has to be equal to q image square, because this has to be 0. And this also has to be true. So that means to say q square a image square is equal to q image square times a square. But if this is true, you can immediately say that this is a image square is equal to a square. This seems to suggest there are 4 solutions. You have q is equal to q image is equal to plus q. Q image is equal to plus q again, and a image could be plus a, and a image could be minus a. But I can have the opposite also, right? Q image could be minus q, and a image could be plus a, image could be minus. Let's see where each of these sit. If the image is plus q, so that's a positive charge, so same charge as q. You want to vary the image is plus q itself. So that means to say that the image is right on top of the object itself, or if you say this is your primary object, the image is sitting right there. But that is not possible, correct? If you do this, this will not satisfy phi of xy. Right? There is no way you can satisfy this condition. So let's say equation boundary condition, right? Equation for the boundary condition. The boundary condition means that the electric potential has to be 0. So let me say this is case 1, case 2, case 3, case 4. 1 does not satisfy the boundary condition. One might be a little confused about that, but we derived it from there. How can this not satisfy that? That's because we squared this quantity. Right? When we squared this, we lost some information there. So some solutions that doesn't satisfy that seeped in. What about image charge being plus q at minus a? That's the same thing. Even if you were to put a plus a there, it's the same thing here. If this is this quantity doesn't change, then again it doesn't satisfy the condition. So this is also does not satisfy. Because of the same reason that it's like saying two positive charges, how can it cancel out to give you a 0? If there are two positive charges, there will be two positive potentials. At this point, two positive numbers cannot be 0. So these two solutions are spurious. Spurious in the sense it led to the spurious solutions when we neglected this negative sign. Any questions this point? Why it was? Okay. So what about 3? You're saying image charge is minus q, but it is positioned at plus a. That means to say that this is plus q and you place a negative charge on top of that. And yes, that is correct. That is a correct solution. But then the electric potential is 0 everywhere. So it is sort of a trivial solution. So this means that phi is 0 everywhere, not just on the surface. It is phi equal to 0 everywhere. So in a sense, it is trivial solution. It's not very interesting. And finally, there is 4th solution, which is what we are interested in, that image charge is minus q. So let me write that as this is minus. So this is equal to exactly minus q. And it is exactly the same distance behind inside the conductor if you want, but we want to remove the conductor completely. So this is okay. 4th one is okay. So what we have is that whenever we are doing a conductor, what we are going to do is that just replace it with a negative charge, and we will actually calculate now. Now we have made sure that its boundary condition is satisfied. Now we'll calculate the electric potential, take the derivative of that, calculate the electric field. In fact, we will notice that it is very easy to calculate the charge density on this. That doesn't seem very obvious as to how do you know how much charge has been. And the basic idea is that once you know the electric field, Gauss's law tells you the charge density. Once you know, so the procedure would be calculate phi everywhere, then calculate electric field, which is just gradient of phi. Notice all this information is valid only for z greater than 0. For z less than 0, we have an answer using this solution, but we don't want to use it because that's inside the conductor, that's 0, right? That's our condition. And this is also, we want to keep, sorry, z greater than 0. And for charge density, so on the surface, right, it will be a surface charge density would be equal to, interestingly, or using Gauss's law, simply calculate del dotted with E, right? Divergence of the electric field gives you the charge density. And once you have that, we can calculate the force. Force and interaction energy, everything. All that goes through. In fact, we will see that the force on this conductor is exactly the same as the force on this charge. Like that's simple, right? We know what exactly is the force on this. It is 2 times A, right? Q1, Q2 using Coulomb's law, we know that. In fact, that's exactly the force that is on the conductor. But it's not very obvious at this point as to why should that be. So we will see why that should be. An interaction energy between this charge and the conductor is the same as the interaction energy between this charge and this image. All that we will prove. In fact, at this point, we can, now that we know 1, we can put in 1 more charge, right? So what will happen if you were to have 1 more charge? Again, there is a conductor now. We put in 2 charges. That's the same as having 2 objects, right? 2 images are formed. The same procedure. Go the same distance behind. A negative charge, and this has a negative charge here. But notice now this will also interact with it When we are talking about potential energy or force, remove the conductor, whatever is the configuration now, it's 4 charges, everything works. Like this will repel that, this will repel that actually. Like this negative charge will repel that, this will attract that, and these two will repel. So the whole of electrostatics of point charges comes in for a perfect conductor, especially if it is a planar, it is very immediate. It's of interest, I'll just mention it, we won't do this most probably. If you have a sphere, so think of this is to be now conductor, so phi, this is a perfect conductor. So this is conductor, so phi is equal to 0. So this is a grounded conductor, and now again you can ask the question that if you put a positive charge in here, so this is a grounded conductor. If I put a positive charge here, again one can expect there will be negative charges that will be pulled onto this. So there will be negative charges in there. And it's not very obvious, will this all be negative or will there be some positive charges? Because it is grounded, it will be actually all negative charges. Right? But less dense on this side. And again, the question is, can you replace this whole thing with a single point charge and simulate a conductor? And it turns out, yes, it can be. In fact, it is along the line connecting them, and it's likely. So if this was radius r, and if this was radius a is greater than r, so it turns out to be that the image distance, r image, is equal to, it has to be less, so it is r over a, and it has to have the dimensions of distance, so you multiply by r over a. In fact, if you notice, or if you're familiar with the geometry of a sphere, this transformation is called an inversion transformation. Right? You can think of the whole world outside the conductor being having an image of that inside a sphere. That's called an inversion transformation. It's very well studied in mathematics, and it has a lot of nice properties. So all those properties come inside for a conductor. Most probably we won't be doing this. I will see how much time we have as we go, but we will restrict ourselves to planar. You'll see this probably in another physics course as you go ahead. At this point, I'll stop and we'll come back tomorrow and do the details of the potential and so on. And one can also think of some reflections here. If this was actually a dielectric function, we can actually think of even refraction of the electric field at this point, not the light. But electric field is pretty much what light is built out of. So it's the same properties that happen in light also. Okay, that's all.